Our cosmos conceals far more than it reveals. The physicist Carl Sagan once said that somewhere, something incredible is waiting to be known. This journey takes us into the enigmatic realm of space-time, where our most powerful tools, from giant telescopes to sensitive particle detectors, are constantly challenged by phenomena that defy simple explanation. What if the universe's deepest secrets lie just beyond our current grasp? We will explore 31 mind-bending cosmic mysteries, from the strange fate of information in black holes to the invisible force accelerating the universe. By the end, you will understand how these puzzles are reshaping our very quest for knowledge and what they reveal about the limits of human observation. How much of reality do you think remains hidden from our view? A book filled with stories and knowledge tumbles through the void and crosses the boundary of a black hole. According to Einstein's general relativity, that book is gone forever, crushed into a single point of infinite density. Its information, the very essence of its existence, seems to have been erased from our universe. This is the heart of the black hole information paradox, a fundamental clash between the two pillars of modern physics. Quantum mechanics insists that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. General relativity, with its serene description of space-time warping into a one-way trap, suggests otherwise. For decades, this conflict remained a deep, theoretical fissure. The great physicist Stephen Hawking initially sided with Einstein's equations, famously arguing that information swallowed by a black hole is irretrievably lost, evaporated away into a featureless form of energy now known as Hawking radiation. This was a shocking proposal, as it implied that the universe is fundamentally unpredictable, that its past does not neatly determine its future. How could physics function if the history of objects simply vanishes? Other theorists like Leonard Susskind fought this idea fiercely. They argued for a cosmic loophole, a way for information to be preserved. Perhaps the information from our fallen book is not destroyed. Maybe it is encoded on the surface of the black hole's event horizon, the point of no return, like a hologram. Later, this information could be slowly and chaotically radiated back out into the universe through Hawking radiation. Think of it like burning a book. To our eyes, the information is lost in the flames, but in reality, every detail is preserved in the pattern of the smoke, the chemistry of the ashes, and the heat emitted. The information is fantastically difficult to reconstruct, but it is not gone. This led to another dizzying idea, the firewall paradox. If information is being encoded and radiated, it might require a wall of intense energy right at the event horizon, incinerating anything that falls in. This directly contradicts general relativity, which predicts an astronaut crossing the event horizon would feel nothing unusual at all. So we are left with a profound question. Does the universe truly allow information to vanish into nothingness, or is our understanding of space and time simply incomplete? This paradox shows us that at the very edge of observation, where our telescopes cannot peer, the laws of physics as we know them begin to fray. Just as one cosmic riddle challenges our understanding of information, another haunts the very structure of the universe itself. Dark matter is the invisible scaffolding holding up a cosmic cathedral, a presence we can feel through its immense gravitational pull but have never directly seen. This profound mystery began to take shape in the 1970s with the work of astronomer Vera Rubin. She was studying the rotation of spiral galaxies, expecting the stars at the outer edges to move slower than those near the bright center. just as Pluto orbits our Sun more slowly than Earth. But her observations revealed something astonishing. The stars far out in the galactic suburbs were whipping around at nearly the same high speed as the inner stars. This could mean only one thing. Those galaxies contained far more mass than their visible stars and gas could account for, all of it generating a powerful gravitational grip from the shadows. This unseen source, this cosmic glue, is what we now call dark matter. It is a substance that does not emit, absorb, or reflect any light, making it completely undetectable to our most powerful telescopes. It simply does not interact with electromagnetic force. According to detailed measurements from the Planck Space Observatory collaboration, this mysterious substance is not a minor component. It makes up about 27% of the entire mass-energy content of the universe. All the stars, planets, and galaxies we can see are just a tiny fraction, floating in a vast, unseen ocean of dark matter. So what could it possibly be? The leading candidates are hypothetical particles that lie far beyond the standard model of particle physics. One prominent idea is WIMP, or weakly interacting massive particles. These would be heavy particles that rarely interact with normal matter, only making their presence known through gravity. Another candidate is the action, an extremely light particle theorized to solve a different problem in quantum physics. For decades, scientists have built exquisitely sensitive experiments deep underground to shield them from cosmic rays, hoping to catch the rare bump of a dark matter particle colliding with a normal atom. So far, the detectors have remained silent. We also have powerful indirect evidence for dark matter's existence. One of the most compelling examples is gravitational lensing. Einstein's theory tells us that mass bends the fabric of space-time. When light from a distant galaxy travels through a region of dark matter, its path is warped, distorting the galaxy's image like a funhouse mirror. By mapping these distortions, astronomers can chart the distribution of the invisible mass causing them. Then there is the bullet cluster, a spectacular collision of two galaxy clusters. Observations show that the hot gas from the clusters, the normal matter, slammed into each other and slowed down, but the dark matter, deduced from its gravitational lensing effect, sailed right through the collision, completely separate from the gas. This proves dark matter is not just a misunderstanding of gravity. It is a real, physical substance that does not interact like anything we know. What if dark matter is composed of particles our most advanced colliders cannot yet create? This enigma pushes observational science to its absolute limits, forcing us to acknowledge that most of the universe's mass is made of something we cannot see. While dark matter pulls the cosmos together, a far more dominant and mysterious force is actively tearing it apart. In 1998, two independent teams of astronomers, one led by Saul Perlmutter and another by Brian Schmidt and Adam Rees, were observing distant stellar explosions known as Type I, a supernova. These supernovae act as cosmic mile markers, their standard brightness revealing their true distance. Both teams expected to confirm that the universe's expansion, born from the Big Bang, was gradually slowing down due to the collective gravity of all matter. Instead, they uncovered the opposite. The most far-flung supernovae were significantly dimmer than predicted, meaning they were much farther away than anyone had calculated. The only possible explanation was that the expansion of the universe was not slowing at all, but accelerating, as if some unseen repulsive force was pushing galaxies apart at an ever-increasing rate. This discovery was so shocking and profound it earned the teams the Nobel Prize in Physics in 2011. Adam Rees later described the moment of realization as a period of genuine terror and amazement, terrified they had made a mistake but amazed by the potential implications. This mysterious force driving the acceleration was named dark energy. Calculations now show that dark energy constitutes a staggering 68% of the entire mass energy content of the universe, making it the dominant component of reality. It is the prime architect of cosmic fate. The leading theoretical candidate for dark energy is something Einstein himself proposed, and then later discarded as his greatest blunder, the cosmological constant. This is a term in his equations of general relativity that represents a constant energy density permeating the vacuum of space itself. Think of empty space not as truly empty, but as a seething foam of virtual particles popping in and out of existence, each pair contributing a tiny bit of repulsive energy. Across the vast volumes of the cosmos, this vacuum energy adds up to an immense, smooth force that counteracts gravity. A simple analogy is blowing up a balloon. If you start inflating it and then it suddenly begins expanding faster on its own, stretching its own rubber, you would know something strange is at work inside. That is precisely what dark energy is doing to the fabric of space-time. This discovery directly shapes predictions for the ultimate fate of the universe. If dark energy remains constant, the acceleration will continue forever, leading to a cold, dark, and isolated end known as the heat death, where galaxies are pulled so far apart that the sky goes black. But a crucial question remains, one that challenges our long-term observational capabilities. Is dark energy truly a constant force, as the cosmological constant suggests, or does its strength change over time? Answering this requires measuring the expansion rate with incredible precision across billions of years, a task that pushes our finest instruments, like the Hubble and James Webb Space Telescopes, to their absolute limits. This phenomenon stretches our understanding of cosmic dynamics to the breaking point, forcing us to confront the fact that the universe is dominated by something we cannot comprehend, preparing us for yet another profound observational puzzle. Two particles are born together, intimately linked in a quantum embrace, and then flung to opposite ends of the galaxy. Yet, the moment you observe one and force it to choose a specific state, its distant partner instantly snaps into a corresponding state, as if connected by an invisible thread. This is not science fiction. This is quantum entanglement, a bizarre and fundamental property of our universe that Albert Einstein himself found so unsettling he famously derided it as spooky action at a distance. He believed the universe should be local, meaning no influence could travel faster than light, and that objects should have definite properties regardless of whether we are looking at them. Entanglement seemed to violate both these principles. It suggested a profound interconnectedness that defied the very fabric of space and time. For decades, it remained a philosophical debate, a troubling paradox in the mathematics. Then came physicists like John Stuart Bell, who devised a way to test if these spooky correlations were real or if some hidden classical variable was at work. Experiments by pioneers such as Anton Zeilinger have since confirmed with undeniable precision that entanglement is real. The universe is genuinely spooky. The magic begins with a concept called superposition. A quantum particle, like an electron or a photon, can exist in a blend of all its possible states simultaneously, like a spinning coin that is both heads and tails at once. This fragile coexistence lasts only until a measurement is made, forcing the coin to land. When two particles are entangled, their fates are woven together. They are described by a single, shared quantum state. Measuring one particle here on Earth doesn't just reveal its property, it instantly defines the property of its partner, perhaps on the other side of the observable universe. This challenges our deepest notions of locality and causality. How can information seem to travel instantaneously? The key is that no usable information is actually sent. You cannot force your particle into a state to send a message to the other side. The correlation only becomes apparent when the two observers later compare their results through a normal, slower-than-light channel. It is as if you and a friend each took one glove from a pair without looking, then traveled to different continents. The moment you open your box and see a left-handed glove, you know with certainty your friend has the right. The gloves were always a matched set, their outcome predetermined. But in the quantum world, the gloves did not have a definite handedness until you looked. This distinction was the heart of the debate, and Bell's theorem provided a mathematical way to tell the difference. The experiments have consistently shown that the universe chooses the quantum version. The gloves truly have no defined handedness until the very moment of observation. This profound mystery is not just a theoretical curiosity. It is the foundation for emerging technologies like quantum computing, where entangled bits or qubits can perform vast calculations in parallel. It also enables quantum cryptography, creating theoretically unbreakable codes because any attempt to eavesdrop on an entangled signal would instantly disturb the fragile quantum state, alerting the users. Scientists have even demonstrated quantum teleportation, not of matter, but of the quantum state of a particle across significant distances using an entangled pair as a resource. So, does this spooky connection imply we are missing a deeper layer of reality, one where space and time are not the fundamental stage but emergent properties from a vast underlying quantum network? Entanglement forces us to confront the limits of observation itself, revealing a cosmos far more interconnected than our classical senses could ever perceive. The entire sky glows with a faint, uniform heat, the cooled remnant of the universe's fiery birth. This cosmic microwave background radiation is the oldest light we can see, a snapshot of the cosmos when it was just 380,000 years old. And it presents a profound puzzle. No matter which direction we look, from one edge of the observable universe to the other, this ancient afterglow has the same temperature to an astonishing degree of precision. This should be impossible. Think of 2 cups of coffee placed on opposite sides of a vast, cold room. Left to themselves, they would never reach the exact same temperature unless something had stirred them together. In the early universe, the regions of space that produced the light we see in the east and the light we see in the west were too far apart for light or heat to have ever traveled between them. They were beyond each other's cosmic horizon, forever out of touch. So how did they coordinate their temperature so perfectly? This is the horizon problem, a fundamental flaw in the standard Big Bang model. The universe simply should not be this smooth. In the early 1980s, physicist Alan Guth proposed a radical solution: cosmic inflation. He suggested that a fraction of a second after the beginning, the universe underwent a breathtaking, exponential growth spurt, doubling in size over and over again in an unimaginably short time. Before inflation, the entire observable universe was a tiny, subatomic patch that had plenty of time to reach a uniform temperature, just like a small cup of coffee cools evenly. Then inflation happened, stretching this tiny, smooth patch to a size larger than our entire visible cosmos. The entire sky looks uniform because it all came from one little, well-mixed neighborhood. This single idea also solved 2 other major puzzles. It explained the flatness problem, why the geometry of our universe appears so perfectly balanced between expanding forever and collapsing back in on itself. Inflation would have stretched space so much that any initial curvature would be flattened out, like blowing up a balloon to an enormous size so that any small patch on its surface appears flat. It also resolved the monopole problem. Grand unified theories predicted that bizarre, heavy magnetic monopoles, particles with a single magnetic pole, should have been created in abundance in the hot, early universe. They should be everywhere, yet we have never found one. Inflation would have diluted them to near invisibility, sweeping them so far apart that they are effectively gone from our observable realm. The Planck satellite's exquisitely detailed map of the cosmic microwave background provides strong, though indirect, evidence for this theory, revealing tiny fluctuations in temperature that are exactly the kind of seeds inflation would have planted to later grow into galaxies. But without this brief, violent burst of expansion, how do we explain the cosmic order we see? The horizon problem forces us to accept that the observable universe is just a tiny, remarkably uniform piece of a much larger and more mysterious whole, a reality whose true beginnings remain just beyond the horizon of our observation. A cat sealed in a box with a radioactive atom is both completely alive and utterly dead until someone lifts the lid to look. This famous thought experiment by Erwin Schrödinger was not meant to be taken literally, but to highlight the sheer absurdity of applying quantum rules to the everyday world. It points directly to one of the most profound and unsettling questions in all of science, the measurement problem. At its heart, this problem asks a deceptively simple question: what actually happens when we observe a quantum system? Why does the act of measurement force a particle, which exists in a shimmering cloud of possibilities, to suddenly pick one concrete reality? For decades, physicists have been split into opposing camps over the answer. Niels Bohr and the Copenhagen interpretation argued that the wave function, the mathematical description of all possible states, literally collapses into a single outcome the moment a measurement occurs. In this view, the particle had no definite position or state until you looked, and your observation brought it into existence. This introduces a strange divide between the quantum world, governed by probability, and the classical world of definite objects. But what exactly constitutes a measurement? Is it the photographic plate, the human eye, or something deeper like consciousness itself? This line of thinking led some to speculate that the human mind is the ultimate cause of collapse, a proposition that places consciousness at the very center of reality. Dissatisfied with this ambiguity, Hugh Everett proposed a radically different solution, the many worlds interpretation. He suggested that the wave function never collapses at all. Instead, at the moment of measurement, reality itself splits into multiple branches. In one universe, the cat is alive and well. In another, it is not. Every possible outcome of every quantum event actually occurs, but we only experience one thread of an endlessly branching multiverse. This eliminates the need for a special observer, but at the cost of an almost unimaginable cosmic proliferation. How can we test such an idea? The classic double-slit experiment demonstrates the core weirdness. When you fire particles like electrons at a barrier with two slits, they behave like waves, creating an interference pattern on the detector screen behind it, as if each electron passes through both slits at once. But the moment you place a device to observe which slit an electron goes through, the interference pattern vanishes. The electrons begin behaving like well-behaved little bullets, going through one slit or the other. The mere act of trying to see the process forces the system to choose a classical path. Even stranger are quantum eraser experiments. These setups allow scientists to seemingly erase the which path information after the particles have already finished their journey and hit the detector. Astonishingly, the interference pattern can reappear, as if the present observation can retroactively change the past behavior of the particle. This is not time travel, but a profound demonstration that the concepts of cause and effect become blurred in the quantum realm. A more modern explanation for why the quantum world seems to vanish is a process called decoherence. This suggests that quantum systems are not collapsed by conscious observers, but simply become entangled with their unpredictable environment. The fragile superposition leaks out, interacting with countless air molecules, photons, and other particles, effectively scrambling the quantum information and making the system appear classical to us. So, are we active participants in creating the reality we perceive, or are we just one thread in an infinite tapestry of parallel existences? The measurement problem forces us to confront the very nature of existence, revealing that the line between the observer and the observed is far more porous than we ever suspected. The silence of the cosmos is deafening, with billions of galaxies, each containing billions of stars, many of which host their own families of planets. The universe should be a vibrant metropolis of intelligent life. Yet, our most sensitive radio telescopes have picked up nothing but the natural background hiss of the cosmos, an unsettling cosmic quiet. This profound contradiction is the Fermi Paradox, a puzzle crystallized by the brilliant physicist Enrico Fermi during a casual lunch conversation in 1950. Looking at the sheer scale of it all, he asked a simple, devastating question. Where is everybody? The numbers seem to be on the side of life. Frank Drake formalized this optimism with his famous equation, a way to estimate the number of communicative civilizations in our galaxy. His calculation considers factors like the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, and the likelihood of life emerging, developing intelligence, and building detectable technology. Even when you plug in conservative numbers, the result suggests that our Milky Way should be teeming with intelligent species. So why does the great cosmic ocean appear so empty and dark? One chilling possibility is the Great Filter hypothesis. This idea suggests that at some point between the emergence of life and the colonization of galaxies, there exists a barrier, a step so difficult that nearly every civilization fails to cross it. The filter could lie in our past, perhaps the jump from simple prokaryotic cells to complex eukaryotic life, which took over 1 billion years on Earth, is exceptionally rare. If that is the case, then we have already passed through the bottleneck, and we might truly be alone. The more terrifying alternative is that the great filter lies in our future. Maybe every advanced civilization eventually discovers a technology, perhaps in particle physics or artificial intelligence, that inevitably leads to its own destruction. Our own silence could be a grim preview of a universal fate. Other theories are less apocalyptic but equally mind-bending. The zoo hypothesis proposes that advanced civilizations are out there, but they have designated our section of the galaxy as a wilderness preserve, deliberately avoiding contact to allow us to develop naturally, much like we observe uncontacted tribes in the Amazon. Or perhaps we are simply not listening correctly. Our searches, like those of the SETI Institute, have primarily focused on radio waves, a technology we mastered a century ago. A civilization only slightly more advanced might use a form of communication we cannot yet conceive of, like neutrino messaging or quantum entanglement, making their chatter completely invisible to our current tools. The recent explosion in exoplanet discoveries, with thousands of worlds now confirmed, tells us that planets are common, but a habitable world does not guarantee a habited one, and a habited one does not guarantee an intelligent civilization. Intelligence itself may not be a winning evolutionary trait in the long run. It could be that the universe is full of life, but almost all of it is microbial or perhaps animal-like, with no species ever developing technology before being wiped out by an asteroid or a supernova. The cosmos might be a vast, silent forest filled with creatures that have learned to hide perfectly. So, are we the first and only ones to gaze at the stars and wonder, or are we surrounded by neighbors who have chosen or been forced into a permanent silence? The Fermi Paradox forces us to confront not just the possibility of other life, but the fragility and potential rarity of our own technological adolescence, a mystery that echoes into the next great challenge of cosmic observation. A shattered egg never spontaneously reassembles itself, its yolk and white leaping back into the shell. This simple, everyday truth points to one of the deepest mysteries in physics, the arrow of time. We all feel time flowing in one direction, an irreversible current from the past to the future. Yet, the fundamental laws of physics, from Newton's mechanics to Einstein's relativity and even quantum theory, are almost perfectly symmetric in time. If you watched a film of two planets orbiting each other, you would not be able to tell if it was playing forward or backward. The equations work just as well either way. So why does our universe exhibit such a strong, one-way direction? The answer appears to lie not in the laws of motion, but in a single, powerful concept, entropy. Often described as a measure of disorder, entropy is more accurately a measure of the number of ways a system's components can be rearranged without changing its overall appearance. A pristine egg has low entropy, its molecules arranged in a very specific, delicate order. A smashed egg on the floor has high entropy, its molecules scattered in a vast number of indistinguishable, messy configurations. The second law of thermodynamics states that the total entropy of an isolated system always increases over time, or at best remains constant. It is the only physical law that gives a clear direction to time. This is why we remember the past but not the future, why we grow older, and why we never see a pile of ashes spontaneously form into a log and leap back into a fireplace. The physicist Sean Carroll frames the ultimate puzzle not as why entropy increases, but why it was ever so low to begin with. The arrow of time, therefore, is not a property of the tiny interactions between particles, but a cosmic-scale feature inherited from the specific initial condition of our universe. The Big Bang must have been a state of extraordinarily low entropy, an incredibly ordered and unlikely starting point. From that pristine beginning, the universe has been evolving toward higher and higher states of disorder ever since, and we are carried along on that inevitable tide. This connects the arrow of time directly to the expansion of the universe and even to the nature of gravity. Gravity takes a smooth, uniform cloud of gas, a high entropy state for particles, and clumps it into stars and galaxies, which are actually lower entropy states. This seems contradictory, but the overall entropy of the universe still increases because the gravitational collapse releases immense heat and radiation, increasing the total disorder. Our psychological experience of time, the feeling of a present moment flowing into the next, may also be a direct consequence of this thermodynamic process, a story our brains tell us as they process information in an entropy-increasing universe. So, is the flow of time a fundamental feature of reality, or is it an emergent illusion, a side effect of our particular cosmic circumstances? If we could observe a hypothetical universe that started in a state of maximum entropy, it would be a featureless, lukewarm soup where nothing ever happens, and the concepts of past and future would have no meaning. Our ability to observe change, to witness the birth of stars and the unfolding of life, is entirely dependent on that one mysterious, low-entropy beginning. This profound link between the cosmic and the commonplace challenges our very perception of temporal observation, forcing us to wonder if the relentless forward march of time is the universe's greatest and most fundamental illusion. Our universe may be a single bubble adrift in an endless cosmic foam. This breathtaking idea emerges directly from the theory of cosmic inflation, a concept that solves fundamental puzzles about our own cosmos while opening a door to an even grander reality. We have already seen how inflation explains the remarkable uniformity of the cosmic microwave background, stretching a tiny, smooth patch into our entire observable universe. But what if that inflationary expansion did not stop everywhere at once? This is the heart of eternal inflation, a model championed by physicists like Andre Linde. He proposed that the vacuum energy driving inflation is not a single entity but a landscape of different possible states. Think of it like a vast, rolling hillside covered in valleys. Our universe settled into one low-energy valley, allowing inflation to end and stars to form. But other regions of space-time remain stuck on the high plateaus, where the repulsive energy is immense, causing them to hyper-inflate at a rate that defies comprehension. In these runaway regions, new pocket universes are constantly budding off, each with its own separate space-time and potentially its own unique laws of physics. Our entire cosmic history, from the Big Bang to the present day, might just be the local story inside one of these countless bubbles within an eternally expanding multiverse. The evidence for the initial inflationary burst in our own bubble is etched into the cosmic microwave background. The subtle patterns of hot and cold spots observed by satellites like Planck are precisely the kind of quantum fingerprints that a rapid expansion would leave behind, tiny seeds that would one day grow into the vast cosmic web of galaxies. But the step from inflation to a multiverse involves a deeper layer, often tied to string theory. This theoretical framework suggests a staggering number of possible stable configurations for the extra dimensions it proposes, perhaps 10 to the 500 different versions. Each configuration corresponds to a different vacuum state, a different valley in the landscape, and potentially a different bubble universe with its own constants of nature. In one bubble, the strength of gravity might be 1,000 times stronger, making stars burn out in a blink. In another, electromagnetism might be too weak to form atoms, preventing chemistry and life as we know it. We happen to inhabit a bubble where the numbers are just right, a concept that some argue answers the question of why our universe seems so finely tuned for our existence. The challenge, of course, is one of observation. If other universes are forever beyond our cosmological horizon, causally disconnected from us, how can we ever claim they are real? Some scientists propose looking for subtle imprints on our own cosmos, perhaps a strange cold spot in the microwave background caused by a gravitational tug from a neighboring bubble long ago. Others suggest that the very laws of physics in our universe might be the only evidence we need, their unlikely perfection hinting at a broader evolutionary process across the multiverse. Does the multiverse represent the ultimate limit of scientific inquiry, a realm of untestable speculation? Or is it the next great frontier, forcing us to redefine what we mean by evidence and observation in a cosmos of infinite possibilities? Gravity feels feeble, almost irrelevant, in the world of the very small. The force that holds entire galaxies together is 1,000,000,000,000,000,000,000 times weaker than the electromagnetic force that binds atoms. It is the difference between an ant trying to move a mountain and a colossal giant effortlessly pushing it aside. This staggering imbalance lies at the heart of the hierarchy problem, one of the most perplexing issues in all of particle physics. The puzzle centers on the Higgs boson, the particle discovered at the Large Hadron Collider that gives all other fundamental particles their mass. Its own mass is about 125 times the mass of a proton. While that sounds substantial, to a physicist it is alarmingly light, especially when compared to the Planck scale, the energy level at which gravity becomes as strong as the other forces. The Higgs mass should naturally be driven up to this immense Planck scale by its interactions with every other particle in the universe through quantum fluctuations. Think of the Higgs field as a celebrity constantly surrounded by a crowd of paparazzi. The jostling and pushing of the crowd, these quantum corrections, should violently shove the celebrity's status, its mass, to an unbearably high level. Yet when we observe it, the Higgs is remarkably calm and lightweight. How does it stay so pristine amidst the chaos? This seems to require an absurdly precise level of fine-tuning, like balancing a pencil perfectly on its tip for billions of years. The slightest nudge should topple it, yet it remains. This unnatural stability suggests our understanding is incomplete. Theorists like Lisa Randall have explored breathtaking solutions. One compelling idea is that gravity only seems weak because it is not confined to our three-dimensional space like the other forces. It could be leaking into extra, unseen spatial dimensions, its strength diluted across a broader reality. In this view, the Planck scale is not so distant, and the hierarchy problem simply vanishes. Another leading candidate is supersymmetry, an elegant theory that proposes every known particle has a much heavier superpartner twin. These supersymmetric particles would cancel out the quantum corrections to the Higgs mass with perfect mathematical harmony, making its lightness natural and expected. The relentless search for these particles has been a primary goal for the Large Hadron Collider. So far, the detectors have not found them, pushing the possible mass of these superpartners to ever higher, more troubling ranges. This leaves us with a profound question. Is the universe we observe a product of incredible cosmic luck, fine-tuned just right for atoms, stars, and ultimately us to exist, an idea known as the Anthropic Principle? Or are we on the cusp of discovering a hidden symmetry of reality, perhaps woven through dimensions we cannot yet perceive? The hierarchy problem is a direct challenge, a whisper from the quantum void that our most powerful colliders might still be blind to the deepest layers of cosmic architecture. The theoretical ocean of energy contained in empty space should be immense, a raging torrent of power capable of tearing the cosmos to shreds in an instant. Yet when we look out at the universe, we see only a placid, barely noticeable puddle. This shocking miscalculation is known as the Vacuum Catastrophe, and it represents perhaps the single greatest failure of prediction in the history of science. Quantum field theory, our most successful framework for describing the subatomic world, calculates the energy density of the vacuum. It does this by summing up all the fleeting quantum fluctuations, the virtual particles that pop in and out of existence in what we call empty space. The result is a number of such staggering magnitude it defies comprehension, one followed by 120 zeros. This is the energy the equations insist should be there. But our cosmological measurements of dark energy, the force driving the universe's acceleration, tell a completely different story. The observed vacuum energy is not just a little smaller, it is 120 orders of magnitude smaller. To grasp that scale, if the theoretical prediction were the volume of the entire observable universe, the actual measured value would be smaller than a single proton. This is the cosmological constant problem, a yawning chasm between the microscopic world and the cosmic scale. The physicist Steven Weinberg wrestled deeply with this, noting that such an incredible fine-tuning seems to demand an explanation beyond pure chance. Why is the vacuum energy so exquisitely close to zero, yet not perfectly zero? This is where the concept of renormalization comes in. In quantum field theory, physicists use mathematical tricks to subtract away infinite quantities and get sensible, finite answers for particle interactions. But the vacuum energy is different. It is a constant background that permeates all of space, and it cannot be simply renormalized away. Its value is a direct input into Einstein's equations for general relativity, and its tiny observed value is what we call the cosmological constant. Proposed solutions only deepen the mystery. One idea is quintessence, a dynamic energy field that changes over time. Perhaps the vacuum energy was not always this small, and we simply live at a fortunate epoch when it has decayed to a negligible value. This would be another form of anthropic reasoning, the suggestion that we observe these peculiar constants only because they allow for our existence. The vacuum catastrophe forces a humbling realization. Our two most powerful theories, quantum mechanics and general relativity, are giving us wildly different answers about the nature of nothingness itself. Is empty space truly alive with a seething, invisible energy that our math cannot yet properly capture? Or does this incredible discrepancy point toward a deeper, more unified theory of quantum gravity, one that will finally reveal why our universe is so much quieter than it has any right to be? Deep in the cold, dark expanse beyond Jupiter, two robotic explorers were subtly drifting off course. The Pioneer 10 and Pioneer 11 spacecraft, after completing their historic missions to the outer planets, were on their way out of the solar system. But as scientists tracked their faint radio signals, they noticed something deeply perplexing. Both spacecraft were experiencing a tiny, unexplained deceleration, an almost imperceptible pullback toward the Sun. This was the Pioneer Anomaly, a mystery that would haunt orbital mechanics for decades. The numbers were minuscule, equivalent to a 10 billionth of the gravity you feel on Earth. But in the precise realm of celestial navigation, even a whisper of unaccounted force demanded an explanation. NASA researchers first suspected a mundane cause, perhaps a software bug or a miscalculation of the gentle push from solar radiation. John Anderson, who led the investigation, later described the team's growing fascination with this stubborn, tiny signal that refused to go away. For years, the most promising explanation was thermal radiation. The plutonium in the spacecraft's power generators produced heat, which the spacecraft radiated away into space. The key was asymmetry. If one side of the complex spacecraft structure radiated just a little more heat than the other, that recoil force could act like a faint, constant brake. Think of a garden hose. When the water sprays out, it pushes back against your hand. Now imagine that on a microscopic scale, with photons of heat acting as the water, providing a tiny but persistent thrust. Meticulous computer modeling was required to account for every bolt, every panel, and every circuit, tracing how heat flowed through the aging probes. The painstaking work eventually confirmed that asymmetric thermal radiation was indeed the primary culprit, solving a mystery that had persisted for over 30 years. Yet, even after this triumph of careful analysis, a tiny fraction of the anomalous acceleration remained unaccounted for, a ghost in the data that some scientists believe hints at more exotic physics. This case is a masterclass in scientific humility, showing how the universe tests us not only with grand, flashy paradoxes, but with quiet, subtle whispers in the data. How many other tiny anomalies are hidden within the flight paths of our distant probes, or in the spin of distant pulsars, waiting for a new generation of observers with sharper eyes to uncover their secrets? A single, powerful shout seemed to ring out from the cosmic static. On August 15, 1977, a radio telescope known as the Big Ear was silently scanning the sky for Ohio State University. Its computer printout, a long scroll of letters and numbers representing signal strength, was mostly a study in quiet. But one sequence of characters was so extraordinary it compelled astronomer Jerry Amon to circle it in red pen and write a single, emphatic word beside it: wow. This 72-second burst was a strong, narrowband signal, precisely the kind theorists predicted an artificial, extraterrestrial transmission would be. It came from the direction of the constellation Sagittarius, and it has never been heard again. Jerry Amon himself later reflected on its strangeness, stating that it bore all the hallmarks of an interstellar broadcast, a signal that seemed too perfect to be natural. The specific frequency it used, around 1420 MHz, is a protected band, a quiet channel where earthly transmissions are forbidden, right next to the natural emission line of hydrogen, the most common element in the universe. It was as if someone had chosen the cosmic equivalent of a clear, open frequency to send a message. Decades of follow-up observations have yielded nothing but silence, turning this one event into a legendary enigma. Skeptics have proposed natural explanations, such as a signal reflected from a piece of space debris or emissions from a passing comet, but none have convincingly matched the unique properties of the WOW signal. The comet theory, for instance, fell apart because the specific comets proposed were not in that region of the sky at that exact time. This singular event underscores the immense challenge of distinguishing a true alien signal from the countless sources of radio interference that flood our modern world, from passing satellites to earthly microwave ovens. It is the ultimate cosmic tease, like hearing your name called perfectly clearly just once in a roaring, crowded stadium, only to turn and find no one there. So, was this a fleeting, one-time greeting from a distant civilization, a cosmic flare that we were simply lucky to catch? Or does its enduring mystery reveal the profound limitations of our search strategies, which rely on listening at the right place, at the right time, and on the right frequency, all at once? The WOW signal remains a haunting lesson in the difficulty of confirming a phenomenon that refuses to repeat, a ghost in the machine that challenges our methods and fuels our imagination for what might be out there. A flash of invisible light outshines the sun for a single, fleeting millisecond. This is the staggering reality of a fast radio burst, a cosmic scream that crosses billions of light years in a radio whisper so brief it could be missed in a blink. In 2007, astronomer Duncan Lorimer and his team were sifting through archived data from a radio telescope in Australia when they found it, a blast of radio waves so powerful and so short it defied all known categories. He described the moment as one of pure astonishment, a signal that should not have been possible. These FRBs are not just faint static. In that thousandth of a second, a single burst can release more energy than our sun emits over 80 days. The key to understanding their immense distance lies in a concept called dispersion. As these radio waves travel through the sparse gas between galaxies, higher frequencies arrive at our telescopes a fraction of a second before the lower frequencies. This smear, this dispersion measure, acts like a cosmic odometer, telling us just how much intergalactic material the signal has plowed through, confirming these bursts are truly extragalactic, originating from unimaginably far away. The mystery only deepened with the discovery of repeaters. While most FRBs are one-off cataclysmic events, a source known as FRB 121102, located in a dwarf galaxy 3 billion light-years away, fires off bursts irregularly. It crackles back to life without warning, ruling out any source that destroys itself in a single, final explosion. This points toward an object that can survive these immense energy releases, something like a magnetar, a type of neutron star with a magnetic field so intense it could erase a credit card from half the distance to the moon. Theorists suggest that starquakes on a magnetar's crust or flares from its twisted magnetic fields could be the engine. Other possibilities include the violent merger of two neutron stars or matter falling onto a newly formed black hole. The sheer power and brevity of these signals have, of course, sparked more speculative ideas. Could they be the lighthouse beams of interstellar spacecraft, or the deliberate transmissions of an advanced civilization? While this is considered highly unlikely, The fact that we must even entertain the question shows how thoroughly these bursts challenge our astrophysical imagination. What natural cosmic engine can switch on and off with such ferocious, unpredictable power? Capturing these events tests the very limits of our technology, requiring radio telescopes to scan vast swaths of the sky continuously, waiting for another millisecond flash in the cosmic dark. This frantic search for fleeting signals prepares us for an even stranger kind of cosmic rhythm, one that beats with the steady, perfect timing of a metronome. Our galactic neighborhood is caught in a slow, relentless river. The Milky Way, along with our entire local group of galaxies and thousands more, is drifting through the cosmos, not aimlessly, but toward a specific, mysterious point in the darkness. This immense, unseen gravitational anchor is known as the Great Attractor. It lies in the direction of the Centaurus constellation, a region of space so massive it pulls on millions of galaxies, orchestrating a flow across hundreds of millions of light-years. Cosmologists like Alan Dressler, part of the Seven Samurai team that mapped these large-scale flows in the 1980s, described the surprise of discovering that our motion could not be explained by the visible matter alone. We are all part of a vast cosmic current rushing toward a hidden waterfall. The primary method for uncovering this motion comes from painstaking redshift surveys. By measuring how the light from distant galaxies is stretched toward the red end of the spectrum, astronomers can calculate their velocity. When you subtract the general expansion of the universe, a strange pattern emerges, a coherent flow of galaxies all moving in the same direction, like iron filings drawn to a powerful magnet hidden behind a curtain. The greatest challenge to observing this magnet directly is our own galaxy. The Milky Way's equatorial plane is thick with gas and dust, creating a zone of avoidance that blocks our view of the core of the Great Attractor, much like trying to see a distant mountain range through a dense, permanent fog. Peering through this obscuration requires telescopes that operate in wavelengths other than visible light, such as radio and X-ray observatories. These tools have revealed that at the heart of this gravitational anomaly lies the Norma cluster, a dense gathering of galaxies, and beyond it, an even more immense structure known as the Shapley supercluster, one of the largest concentrations of matter in the observable universe. Yet, even the combined mass of all these visible galaxies is not enough to account for the powerful pull we feel. The dominant force must be the gravitational grip of dark matter, woven into a colossal halo that surrounds the entire region. So what truly lies at the center of this cosmic whirlpool? Is it a confluence of dark matter on a scale we can barely comprehend? Or could there be structures there so vast they redefine our understanding of the cosmic web? This mystery forces our technology to its limits, using every trick to see through the galactic dust, reminding us that the greatest pulls in the universe often come from the places we cannot see. Even the oldest light in the universe seems to whisper a secret about our own home. The cosmic microwave background, that pristine fossil from the dawn of time, reveals a pattern so strange and unexpected that cosmologists have given it a dramatic name, the axis of evil. This is not a malevolent force, but a chilling anomaly, a large-scale alignment in the temperature fluctuations of the CMB that appears to be correlated with the plane of our solar system and the direction of our galactic motion. It is as if the universe's earliest imprint somehow knows which way we are looking. Researchers from the Planck satellite collaboration have rigorously confirmed these asymmetries, finding that the hot and cold spots are not scattered as randomly as they should be. Instead, they show a curious preference for a particular axis, a spine running through the cosmos that aligns eerily with our local cosmic neighborhood. This directly challenges one of the most fundamental assumptions in all of cosmology, the cosmological principle. This principle states that on very large scales, the universe is homogeneous and isotropic, meaning it should look the same in every direction and have no preferred center or special axis. The axis of evil suggests this might not be entirely true. The evidence comes from analyzing the CMB's multipole moments, which are mathematical descriptions of the temperature variations at different angular scales. The quadrupole, which describes patterns on a 60-degree scale, and the octupole for 30 degrees, are unusually weak and seem to be aligned with each other along this same mysterious axis. The statistical significance of this alignment is what keeps scientists awake at night, with some analyses suggesting the odds of it happening by pure chance are less than 1 in 1,000. Could this be a colossal fluke? Some argue it might be a subtle systematic error, an artifact of how we subtract the foreground glare of our own galaxy from the CMB data. But if it is real, the implications are staggering. It could hint that the universe is not isotropic on the largest scales we can observe, that it has a grand, woven structure we are only beginning to sense. Perhaps our universe is like a vast crystal with a fundamental grain to its structure that imprints itself on everything, including the first light. Looking at a map of the CMB, you can see this alignment, a subtle but persistent directionality in the splotches of hot and cold that should, by all rights, be oriented purely at random. So is our universe not the perfectly uniform cosmos we have always assumed? Does this faint axis point toward a deeper layer of reality, a cosmic architecture that privileges one direction over another? This alignment forces a profound reevaluation of our most basic cosmological models, suggesting that the very stage upon which the cosmic drama plays out may be tilted in a way we never anticipated. At scales a billion times smaller than an atom, the smooth canvas of space and time might shatter into a chaotic froth. This is the domain of quantum gravity, the ultimate quest to unify Einstein's general relativity with the bizarre rules of quantum mechanics. General relativity paints a beautiful picture of space-time as a continuous, flexible fabric, warped by mass and energy. Quantum mechanics, on the other hand, shows us a granular world where everything is quantized into discrete packets. These two pillars of physics are fundamentally at odds, and their conflict becomes a screaming paradox at the unimaginably tiny Planck scale. Here, both our trusted theories break down completely. The Planck length is about 1.6 times 10 to the negative 35 meters, a size so small that if you magnified an atom to the size of the observable universe, the Planck length would be roughly the height of a single tree. At this scale, the very concepts of before and after, here and there, may lose all meaning. Space might be composed of finite, vibrating loops, as proposed in Carlo Rovelli's loop quantum gravity, or perhaps it is built from tiny, vibrating strings, as string theory suggests. The physicist Lee Smolin describes this as a universe where atoms of space and time weave the dynamic geometry of the world. The challenge of observing such effects is monumental, as the Planck scale is far, far beyond the resolution of any particle collider we could ever build. It would require a machine the size of our galaxy to probe such energies directly. So how can we possibly test these ideas? Scientists look for subtle, indirect signatures. One method involves studying the timing of gamma-ray bursts, the most violent explosions in the universe. If space-time is truly grainy, then photons of different energies traveling across billions of light-years might be delayed by slightly different amounts, as if they were navigating a choppy quantum sea. Another potential laboratory is the evaporation of black holes, where the final moments could reveal information about the discrete structure of space. Think of it like trying to discern the individual pixels on a screen of such incredible resolution that it appears perfectly smooth to your eye. You cannot see the pixels directly, but if you look for subtle artifacts at the very edges of perception, you might detect their presence. What does it mean for reality if space and time are not fundamental, but merely emergent properties of a deeper quantum architecture? This frontier challenges not just our technology, but the very definition of what it means to measure anything at all, forcing us to consider that the stage itself may be an illusion. At the very heart of a black hole, the fabric of reality itself is torn apart. General relativity leads us to a point of infinite density and infinite curvature, a mathematical monstrosity known as a singularity. Here, all known laws of physics cease to function. The great physicist Roger Penrose, with his groundbreaking singularity theorems, demonstrated that under the relentless pull of gravity, the collapse of a massive star inevitably leads to such a point. He argued that this is not a flaw in the math, but a clear signal that we need a new theory, a quantum theory of gravity, to describe these most extreme conditions. The equations of Einstein break down because they cannot handle infinity. An infinite density means all the mass of a star, sometimes millions of times the mass of our Sun, is crushed into a point with zero volume. This is not just an extreme environment, it is a place where the very concepts of here and now lose all meaning. This catastrophic collapse is hidden from our view by the event horizon, the ultimate point of no return. Once matter or light crosses this boundary, it is forever lost to our observable universe, destined to fall toward the central singularity. This leads to the cosmic censorship hypothesis, a profound idea suggesting that nature abhors a naked singularity. The proposal is that every singularity is always modestly clothed by an event horizon, protecting the outside universe from its unpredictable and lawless core. Without this cosmic curtain, the cause and effect that structure our reality could simply vanish. Imagine a region where gravity could fluctuate to infinite strength without warning, where space and time could tie themselves into knots. The universe, it seems, has built a firewall not of fire, but of pure geometry to quarantine this fundamental unpredictability. So what truly happens at the center of a black hole? Does matter reach a genuine infinity, or does it transition into something else entirely, perhaps a gateway to another universe or a new state of existence? The singularity represents the ultimate limit of observation, a place we can never see and can only approach through the fragile power of mathematics. This descent into infinite curvature forces us to confront a reality where our most trusted tools fail, leaving us to wonder if the center of a black hole is not an end, but a transformation so radical it defies our current comprehension. Two of our most trusted cosmic clocks are ticking out of sync. For over a decade, astronomers have been locked in a quiet but escalating conflict over a single number, the Hubble constant, which describes how fast the universe is expanding today. This discrepancy, known as the Hubble Tension, pits our view of the ancient universe against our measurements of the modern cosmos. On one side, we have the exquisitely detailed map of the infant universe provided by the Planck satellite. By analyzing the cosmic microwave background, scientists can run the clock forward from the Big Bang, using our well-tested standard model of cosmology to predict the current expansion rate. This method gives a very precise value of about 67 kilometers per second per megaparsec. On the other side, a team led by Nobel laureate Adam Rees uses the cosmic distance ladder. They observe pulsating stars called Cepheids and Type 1, a supernova in nearby galaxies, to measure distances and velocities directly. Their result is consistently higher, around 73. The difference seems small, but the uncertainty bars no longer overlap. Adam Rees has described this as a growing crack in the foundation of cosmology. It is as if you had two identical, finely engineered watches. One is set by tracing its history back to the moment it was built, and the other is set by checking the current time against a known standard. Both are incredibly precise, yet they stubbornly disagree by several seconds. This is not a simple calibration error, it is a fundamental mismatch. The implications are profound. If the local measurements are correct, it suggests that our standard cosmological model, lambda cold dark matter, is incomplete. Perhaps dark energy is not a constant but has been growing stronger over time, adding an extra push to the expansion. Or maybe neutrinos, those ghostly particles that flood the universe, are more exotic than we thought, with properties that subtly alter the cosmic expansion history. Another tantalizing possibility is that the universe contains a previously unknown type of radiation or a magnetic field that influenced its early growth. Each potential solution requires rewriting a chapter of our cosmic story. So, is this tension merely a collective blind spot in our meticulous observations, a subtle systematic error that has evaded detection in both camps? Or does this persistent disagreement point toward a more exciting truth, that we are on the verge of discovering a new ingredient in the cosmic recipe? The Hubble tension forces a humble acknowledgement that the more precisely we measure the universe, the more it reveals how much we have yet to learn. The universe's first few minutes were a frantic forge for the lightest elements. In that blistering heat, just moments after the Big Bang, protons and neutrons fused to form the primordial nuclei of hydrogen, helium, and a tiny trace of lithium. This process, known as Big Bang nucleosynthesis, provides a precise recipe for how much of each element should have been created. For hydrogen and helium, the predictions match the observed abundances in the oldest stars almost perfectly. But for lithium, the cosmic books do not balance. The models confidently tell us there should be about 3 times as much lithium in the universe as we can actually find. This glaring mismatch is the lithium problem, a quiet but persistent thorn in the side of cosmology. Researchers like Brian Fields have spent decades scrutinizing this discrepancy, searching for the missing piece of nuclear physics that could explain where the lithium went. The evidence comes from the atmospheres of ancient, metal-poor stars, which act as cosmic time capsules preserving the chemical composition of the early universe. When astronomers analyze the spectra of these venerable stars, the fingerprint of lithium is consistently and puzzlingly faint. So where did it all go? One possibility is that the primordial lithium was destroyed inside the very stars we use to measure it. Perhaps these ancient furnaces churned and mixed their material in ways we do not fully understand, dragging surface lithium down into hotter interior layers where it could be fused into heavier elements. Another line of investigation questions the nuclear reaction rates themselves. Could there be unknown resonances or subtle errors in our understanding of how protons and lithium nuclei interact? More exotic solutions have been proposed, involving the decay of hypothetical particles from the early universe that could have altered the delicate nuclear chain. Each potential answer forces us to re-examine the first moments of cosmic creation. Are our models of the Big Bang's first nuclear furnace fundamentally incomplete? This problem is a humbling reminder that even our most successful theories can harbor a deep and unresolved mystery, a chemical ghost from the dawn of time that challenges the very story of our origins. An astronaut floating in the void of deep space feels nothing but the profound cold of the vacuum. Yet, if that same astronaut were to fire their engines and accelerate continuously, something miraculous would happen. They would begin to feel a faint warmth as if bathed in a gentle glow of heat. This is not a malfunction of their suit, but a prediction of quantum field theory known as the Unruh Effect. The physicist William Unruh, who proposed this in 1976, described it as a kind of mirage, a reality that appears only to those who are rushing forward. For an observer moving at a constant velocity, the space remains empty and cold, but for the accelerating astronaut, the empty void seethes with particles. This thermal radiation is created purely by their own motion. The key to understanding this lies in the concept of an event horizon, not of a black hole, but of an accelerating frame. Just as a black hole's event horizon hides information from the outside universe, an accelerating observer is always trailing a region of space from which light can never catch up to them. It is this effective horizon that tricks the quantum fields, causing them to manifest as a bath of warm particles. The temperature of this ghostly glow is incredibly tiny, proportional to the acceleration. To feel even a single degree of warmth above absolute zero, an astronaut would need to accelerate at 1 trillion times the force of gravity on Earth, a rate that would crush them instantly. This makes direct experimental confirmation fantastically difficult. Think of it like a person running through a perfectly still, cold field. To them, the air rushes past, feeling like a chilling wind. But in the Unruh effect, the runner is not feeling a real wind. They are essentially creating warmth from the very act of running through the quantum fields that fill space. This provides a beautiful and profound analogy for Hawking radiation. Just as an accelerating observer creates a thermal bath by rushing away from a region of space, a black hole creates Hawking radiation by its intense gravitational field, which acts like a form of acceleration at its event horizon. Both effects point toward a deeply unsettling idea that particles and temperature are not absolute properties of the universe, but depend on the state of motion of the observer. So, does this mean that reality itself is different for someone in motion? Can the simple act of acceleration truly conjure particles from nothing? Testing such a subtle prediction pushes our experimental ingenuity to the brink, forcing us to design ever more clever ways to listen for the whispers of quantum fields in motion. Einstein remained deeply troubled by the spooky implications of quantum entanglement. In 1935, he collaborated with physicists Boris Podolsky and Nathan Rosen to publish a paper that launched a direct assault on the theory's completeness. Their thought experiment, now known as the Fermi Paradox, was designed to prove that quantum mechanics must be an incomplete description of reality. They argued that if you could know with certainty the outcome of measuring a distant particle without disturbing it, then that particle must have possessed that definite property all along. This, they said, pointed to hidden variables, unseen factors that deterministically govern particle behavior, restoring a common sense, local reality where no spooky influences could travel faster than light. Einstein famously insisted that the moon is there even when nobody is looking, and he could not accept a universe where reality was conjured into existence by the act of observation. Niels Bohr, the staunch defender of quantum orthodoxy, responded with a characteristically subtle rebuttal. He argued that it was meaningless to talk about a particle having a definite position or momentum independently of the specific experimental context used to measure it. The EPR setup, according to Bohr, was not one single phenomenon but two different, mutually exclusive experiments, and you could not mix their results to claim a pre-existing reality. The heart of their thought experiment involved a pair of entangled particles flying apart. If you measure the position of one particle, you can instantly know the exact position of its partner, no matter how far away it has traveled. Alternatively, if you measure the momentum of the first, you know the momentum of the second. The EPR argument was that since you could predict either property with certainty without touching the second particle, it must have had both a definite position and a definite momentum all along, in violation of the quantum uncertainty principle. This seemed to demand a local, hidden reality. For decades, this remained a philosophical debate, a war of ideas fought on paper. Then, in the 1960s, physicist John Stuart Bell found a way to translate the argument into a testable mathematical inequality. He showed that if local hidden variables were real, then the statistical correlations between measurements on entangled particles would have to obey a certain limit. Quantum mechanics, with its spooky connections, predicted violations of this limit. When experimentalists like Elaine Aspect performed these tests in the 1980s, they used delicate setups involving pairs of entangled photons and rapidly switching detectors. The results were unequivocal. The quantum correlations violated Bell's inequality, ruling out local hidden variable theories. The universe had chosen spookiness. Modern quantum optics experiments have confirmed this non-locality with even greater precision, closing potential loopholes. So, what does this mean for our understanding of reality? Are we forced to abandon the comforting idea that the world is local, that objects are only influenced by their immediate surroundings? The Fermi Paradox forces a stark choice. Either the universe is fundamentally non-local, with instantaneous connections woven into its fabric, or it is deterministic but requires information to travel faster than light. Both options challenge our deepest intuitions about space and time, revealing that the very act of observing one particle can define the reality of another across a vast distance, a mystery of correlation that stretches our concept of observation to the breaking point. Why is the night sky so profoundly dark? This simple question, asked on any clear evening, unravels a cosmic mystery that troubled astronomers for centuries. The paradox, named after the German astronomer Heinrich Olbers, poses a stark conflict. If the universe is infinite, static, and filled uniformly with stars, then every line of sight should eventually land on the surface of a star. The entire night sky should be as brilliantly bright as the surface of the sun, a solid wall of starlight. Johannes Kepler saw this as an argument against an infinite universe, believing the dark sky was evidence of a finite cosmic shell. The resolution lies in the dynamic nature of our cosmos, a truth hidden in the darkness itself. The universe is not infinite in age, it is only 13.8 billion years old. This finite age means light from the most distant stars simply has not had enough time to reach us yet. Our observable universe has a horizon, a limit to how far we can see. More profoundly, the expansion of the universe discovered by Edwin Hubble provides the final piece. As space itself stretches, the light from distant galaxies is stretched with it, shifting to longer, redder wavelengths and losing energy. This cosmological redshift effectively cools and dims the light, draining its energy across the vast cosmic distances. The cosmic microwave background is actually the remnant of that primordial glow, but it has been redshifted so dramatically from visible light into the microwave part of the spectrum, rendering it invisible to our eyes. Imagine standing in an infinite forest where every gap between nearby trees is filled by a more distant tree. You would see nothing but a solid wall of wood. The darkness we see between the stars is the gap between those trees, the vast, empty spaces where light has not yet arrived or has been stretched into oblivion. So what does this profound darkness tell us? It is not an emptiness but a history book. The blackness of space is a direct record of the universe's finite age and its relentless expansion. It is the ultimate evidence that we live in a cosmos with a definite beginning and a dynamic future, a reality where our vision is fundamentally limited by the speed of light and the expansion of space itself. This paradox challenges our deepest assumptions about infinity and observation, forcing us to listen to the story told by the silence between the stars. A magnet, no matter how many times you break it, always forms new north and south poles. This simple fact highlights a profound asymmetry in our universe. For over a century, our equations for electromagnetism have been beautifully symmetrical between electricity and magnetism, with one glaring exception. We observe positive and negative electric charges as separate entities, yet we have never found a solitary magnetic charge, a particle with just a north or just a south pole. This hypothetical particle is known as a magnetic monopole. The theoretical foundation for monopoles is surprisingly robust. The physicist Paul Dirac demonstrated that if even a single magnetic monopole existed somewhere in the universe, it would elegantly explain a fundamental mystery: why electric charge always appears in integer multiples of the electron's charge. His calculations showed that the mere existence of a monopole would force electric charge to be quantized, a fact we observe but have no deeper explanation for. This made the search for monopoles a holy grail of particle physics. Grand unified theories which attempt to merge the electromagnetic, weak, and strong nuclear forces almost universally predict that these particles should have been created in unimaginable numbers during the universe's first moments. They would be incredibly heavy, perhaps as massive as a bacterium condensed into a single point, making them more like tiny black holes than typical subatomic particles. So where are they all? Despite decades of meticulous searching, not a single confirmed monopole has ever been detected. Scientists have employed every tool at their disposal. They have scoured ancient rocks and minerals deep underground, searching for tracks that a heavy, charged monopole would leave as it passed through. They have examined material from the ocean floor and even moon rocks, all with no success. Particle accelerators like the Large Hadron Collider have searched for signs of their creation in high-energy collisions, but the energy required to produce one is far beyond our current reach. The most compelling explanation for their absence is cosmic inflation. That brief, hyper-fast expansion of the early universe would have diluted the primordial monopoles to near invisibility, sweeping them so far apart that finding one in our entire observable universe becomes a statistical miracle. It is as if an entire ocean of confetti was scattered across the cosmos, leaving just one piece in a volume of space larger than 1 billion galaxies. So, do these solitary magnetic poles truly exist, or is nature subtly telling us our theories need revision? The relentless, fruitless search for the magnetic monopole forces us to confront the limits of high-energy observation, a quest that leads directly to the hunt for another ghostly, unseen particle. An invisible sea of ghostly particles floods the cosmos, a cosmic echo even more ancient than the light left over from the Big Bang. This is the cosmic neutrino background, a fossil snapshot of the universe when it was just 1 second old. Born from the inferno of the early cosmos, these neutrinos were the first particles to stream freely through space, decoupling from matter long before protons and electrons combined to form the first atoms. Today, they are the most abundant massive particles in the universe, with trillions passing through your body every second without a trace. The physicist John Bockall, a pioneer in solar neutrino research, once described them as the smallest conceivable quantities of reality, tiny packets of almost nothing that hold profound secrets. Detecting this specific primordial sea of neutrinos, however, is a monumental challenge. Their energy is incredibly low, and neutrinos are famously aloof, interacting with normal matter only through the weak nuclear force and gravity. To them, our planet is almost entirely transparent. Catching one of these relics is like trying to hear a single, specific whisper in a roaring, crowded stadium. The hunt relies on new technologies. One promising method is coherent neutrino scattering, a quantum effect where a low-energy neutrino interacts with an entire atomic nucleus at once, giving it a tiny, detectable kick. Future projects like the proposed Ptolemy experiment aim to use ultra-cold, solid-state detectors with unimaginable sensitivity to capture these feeble kicks. They must be placed deep underground to shield them from the constant barrage of cosmic rays that would otherwise drown out the signal. What secrets are locked inside these ghostly particles? They could reveal the conditions of the universe during its first violent second, telling us about the thermodynamics of the Big Bang itself and potentially shedding light on the very mechanism that drove cosmic inflation. They might even help us understand the nature of neutrino mass, a fundamental puzzle in particle physics. Observing this background would be like opening a time capsule from an epoch before the first light we can see, pushing our detectors to sense a whisper from the cosmic dawn. The universe should be a perfect, empty symmetry. For every particle of matter created in the Big Bang, an identical particle of antimatter should have been born, its mirror image with opposite charge. When matter and antimatter meet, they annihilate in a flash of pure energy. If the cosmos began with perfect balance, all of its contents should have mutually destroyed one another, leaving behind a sea of radiation and nothing more. Yet here we are, made of the stuff that survived. This is the Baryon asymmetry problem, one of the most profound imbalances in all of nature. Why is there something rather than nothing at all? The Russian physicist Andrei Sakharov first outlined the three essential conditions needed for such an imbalance to arise. The universe must be out of thermal equilibrium. It must allow for processes that violate the conservation of Baryon number, and it must exhibit a violation of both charge conjugation and parity symmetry, known as CP violation. This last condition is particularly crucial. CP symmetry means that the laws of physics should be the same for a particle and for its mirror image antiparticle. If you filmed a particle interaction and then played it back in a mirror world where all matter was replaced with antimatter, the physics should look identical. But it does not. Experiments like those at CERN with neutral kaons and B mesons have confirmed that certain particles and their antiparticles decay at slightly different rates. It is a tiny fractional difference, a mere 1% deviation in a specific system. But in the furnace of the early universe, that tiny bias could have been the seed for everything we see. Think of a perfectly balanced scale with matter on one side and antimatter on the other. CP violation is like a nearly invisible breath of wind, just enough to make one side imperceptibly heavier, causing the scale to tip. Once that tipping began, a cascade of annihilations would have ensued, wiping out almost all matter and antimatter. But the side with the slight excess would be left behind, the one part in a billion that survived to form galaxies, stars, and planets. So what was the cosmic engine that generated this wind? One leading idea is leptogenesis, where heavy, sterile neutrinos decayed in the early universe, violating CP symmetry and creating a slight excess of leptons over anti-leptons. This lepton asymmetry could then have been converted into a Baryon asymmetry through subtle Sphaleron processes in the electroweak force. Another theory, electroweak baryogenesis, suggests the imbalance was forged during the electroweak phase transition, a moment when the fundamental forces separated, creating bubbles of true vacuum where CP-violating interactions could favor matter. The evidence for this entire story is written in the cosmos itself. The near-total absence of primordial antimatter and the precise ratio of photons to protons in the cosmic microwave background point directly to this ancient, overwhelming victory of matter. So what was the ultimate cause of that first critical tipping of the scales? Was it the decay of an unknown particle or a property of the Higgs field we have not yet measured? This fundamental asymmetry challenges the core of particle physics, forcing us to ask why the universe is built with a preference for existence, an imbalance that leads us directly to another cosmic ghost. The phantom energy hypothesis dares to imagine a far more violent end for the cosmos. What if dark energy is not a constant force, but something that grows stronger over time, an anti-gravity that intensifies with every passing eon? This speculative form of dark energy, known as phantom energy, would possess an equation of state with a value less than -1, a theoretical possibility that physicist Robert Caldwell and his colleagues explored in depth. He described the potential consequences as the most dramatic cosmic doomsday scenario imaginable. In this model, the acceleration of the universe's expansion would not just continue, it would run away exponentially. The repulsive force would become so overwhelming that it would eventually overpower every binding force in nature. First, the cosmic glue of dark matter holding galaxy clusters together would be overcome, sending galaxies flying apart into the endless void. Then the gravitational bonds within individual galaxies would fail, flinging stars into the darkness. In the final, terrifying moments, the phantom energy would tear apart stars and planets themselves. Ultimately, it would rip the very fabric of space-time, shredding atoms, atomic nuclei, and every fundamental particle into disconnected fragments. It is the ultimate cosmic disintegration, a big rip. Think of the universe as a rubber band being stretched. For billions of years, it expands steadily. But with phantom energy, the stretching accelerates until the rubber band is pulled so taut, so violently, that its very molecular bonds snap and it fragments into dust. Current observational data from supernova and the cosmic microwave background do not support this idea. They point toward a cosmological constant. Theoretically, phantom energy is deeply problematic, as it seems to require negative kinetic energy, a concept that leads to instabilities and violations of fundamental energy conditions. It opens the door to bizarre possibilities like negative mass and wormholes. So, is this terrifying phantom real, or is it merely a mathematical ghost in our equations? Contemplating such an extreme fate forces us to test the absolute limits of our dark energy models, pushing our understanding of cosmic destiny to the brink and preparing us for another ghost from the quantum world. Our three-dimensional reality might be nothing more than an elaborate illusion, a cosmic projection from a distant two-dimensional surface. This is the radical proposal of the holographic principle, a concept born from the fiery clash between gravity and quantum mechanics. The story begins with a deep question about black holes. Physicists Leonard Susskind and Gerard T. Hooft realized that when an object falls into a black hole, all of its information, the complete description of every atom, appears to be encoded on the event horizon, the black hole's two-dimensional boundary. They proposed a stunning resolution to the information paradox, suggesting the information is not lost inside but preserved on this surface like a hologram. The universe itself might operate on the same principle. We could be living inside a vast hologram where all the information needed to describe our three-dimensional world is stored on a remote two-dimensional shell. The most concrete realization of this idea comes from string theory, through the anti-de Sitter/conformal field theory correspondence. This mouthful describes a powerful mathematical duality where a gravitational theory in a warped, higher-dimensional space is perfectly equivalent to a quantum field theory without gravity living on its lower-dimensional boundary. It is a dictionary translating between two completely different descriptions of the same reality. This leads to a fundamental limit on how much information any region of space can contain. The entropy or information content of a volume is not proportional to its volume, as you might expect, but to the surface area of its boundary. A black hole represents the maximum possible information density for its size, and its entropy is precisely given by the area of its event horizon. This Bekenstein-Hawking bound suggests that if you keep packing more information into a box, you will eventually form a black hole, and its surface area becomes the ultimate hard drive. Think of watching a spectacular three-dimensional movie. The immersive experience of depth, movement, and solid objects all emerges from data encoded on a flat, two-dimensional film. The holographic principle suggests our universe is like that movie. The solidity of your hand, the vast depth of space, the whirl of galaxies, all could be a magnificent projection from a cosmic film reel we cannot yet see. How could we possibly test such an abstract idea? Scientists are looking for subtle signatures. Some search for noise, a fundamental graininess, in the laser interferometers used to detect gravitational waves, a potential imprint of the underlying pixelated reality. Others analyze the cosmic microwave background for patterns that might reveal the universe's fundamental pixel size. So, is the world we perceive with such vivid solidity merely a shadow on a distant wall? The holographic principle challenges the very nature of dimensionality, forcing us to question if the stage of space itself is an emergent property, a grand illusion that prepares us for the final, foundational mystery of all. A universe that permits time travel would be a chaotic mess of paradoxes and tourists from the future. Yet our equations of general relativity calmly suggest that certain configurations, like traversable wormholes or infinitely long cosmic strings, could warp space-time into closed time-like curves, paths that loop back on themselves and allow travel into the past. So where are all the time travelers? The great physicist Stephen Hawking proposed a witty but profound answer, his chronology protection conjecture. He once remarked that the best evidence we have that time travel is not possible is that we have not been invaded by hordes of tourists from the future. This was more than a joke. It was a serious proposal that the laws of physics actively conspire to prevent time travel, protecting the logical sequence of cause and effect. The mechanism for this cosmic censorship is thought to lie in the quantum realm. Imagine a wormhole, a tunnel through space-time, being manipulated to allow a journey into the past. As a particle travels back, it would interact with its own past self. These interactions would create a feedback loop of energy, a process called quantum vacuum polarization. Virtual particles constantly flashing in and out of existence would be caught in this temporal loop, their energy building up with each cycle. The calculations show this energy would quickly become infinite, creating a devastating surge that would destroy the wormhole or warp the cosmic string beyond use before any paradox could occur. It is like an electrical circuit designed to short itself out the moment a dangerous feedback loop is detected, preserving the integrity of the entire system. This ties into the Novikov self-consistency principle, which argues that any actions taken by a time traveler were always part of history, creating a single, consistent timeline free of paradox. You could travel to the past, but you could never change it, only fulfill it. So does the universe possess built-in safeguards, a fundamental law that prioritizes causal order above all else. This conjecture pushes our observational limits to the brink, forcing us to wonder if the smooth flow of time we experience is not just a feature, but a fiercely protected law of reality. The universe we inhabit might be resting on a fragile foundation, a cosmic state of temporary peace. This is the chilling possibility of the vacuum metastability event, a theoretical doomsday scenario where the very fabric of reality could suddenly and irrevocably transform. Our cosmos might not be in its most stable, lowest energy state. Instead, it could be trapped in a false vacuum, a precarious plateau, and a single quantum event could tip it over the edge into a deeper, more stable valley. Physicist Joseph Licken has framed this not as an immediate threat, but as a profound question about the ultimate fate of the cosmos, noting that the measured mass of the Higgs boson suggests our vacuum might be metastable, not perfectly stable. The process that could trigger this transition is quantum tunneling. Imagine a ball resting in a small, shallow dip on the side of a vast hill. Normally, it stays put. But through the bizarre rules of quantum mechanics, there is a tiny, non-zero probability that the ball could spontaneously tunnel through the hill and roll down into a much deeper, more stable valley. In our universe, that ball is the Higgs field, the energy field that gives particles their mass. If such a quantum tunnel event happened somewhere in space, it would create a bubble of true vacuum. This bubble would not be empty space, but a region with fundamentally different laws of physics, where the Higgs field has a new value. The laws that govern atoms, chemistry, and life itself would be erased within it. The walls of this bubble would expand in all directions at the speed of light. There would be no warning, no flash of light. One moment, reality as we know it would exist, and the next, an expanding sphere of absolute transformation would sweep it away, repainting the cosmos with a new set of physical rules. The likelihood of this happening is governed by the precise masses of the Higgs boson and the top quark. Their measured values place our universe in a precarious zone on the edge of stability. Yet the timescales involved are almost comfortingly long. The expected lifetime for such a decay is many, many times the current age of the universe. So why even consider it? This phenomenon challenges the limits of our long-term predictive power. It forces us to ask if the constants we rely on are truly constant, or if they are merely local bylaws in a cosmos capable of rewriting its own constitution. Is our universe ultimately stable, or are we just living in a prolonged, peaceful moment before an inevitable and silent collapse? This ultimate fragility leads us to the final, foundational mystery that seeks to tie all these threads together. The ultimate boundary of observation may not be a distant galaxy or a quantum particle, but the very nature of reality itself. What if our universe, with all its galaxies, black holes, and conscious life, is nothing more than an elaborate simulation running on the computer of a vastly more advanced civilization? This is not science fiction, but a serious philosophical argument known as the simulation hypothesis, most famously articulated by the philosopher Nick Bostrom. He frames a stark statistical trilemma. He argues that at least one of three propositions must be true. Either advanced civilizations always go extinct before developing the capability to run such simulations, or they have no interest in running them, or we are almost certainly living in one. The reasoning is based on sheer computational power. If a civilization could ever reach a post-human stage, it could harness the energy of stars to power computers of unimaginable scale. It could then run countless simulations of its own ancestral past, each populated with conscious beings who believe their world is real. From a statistical standpoint, if such simulations are possible, the number of simulated minds would vastly outnumber the one original biological civilization. Therefore, it is far more likely that we are one of the countless simulations rather than the single, original reality. This idea has captivated tech visionaries like Elon Musk, who has bluntly stated that the odds we are in base reality are 1 in billions. The reasoning is simple. If you accept that graphics in video games will eventually become indistinguishable from reality, then what separates us from characters in an unfathomably advanced game? We might even look for glitches in our own physics as potential evidence. The bizarre rules of quantum mechanics, where particles exist in blurred superpositions until observed, could be seen as a rendering optimization technique. Why calculate the precise state of every particle in the universe when no one is looking? It saves on processing power. The finite Planck length, the smallest possible unit of space, could be the pixel size of the cosmic display. Even the hard problem of consciousness, the mystery of how subjective experience arises from matter, could be explained if consciousness is simply a fundamental data type in the simulation's programming language. But if we are in a simulation, how could we ever hope to observe the programmers? Any experiment we design, any instrument we build, would itself be part of the simulated code. It would be like a character in a video game trying to hack the computer it is running on. Its tools and thoughts are all confined within the game's own logic. This leads to profound ethical questions. If our reality is simulated, does that make our joys, our sorrows, and our loves any less real? Or does it imply that the creators have a responsibility for the suffering within their creation? The simulation hypothesis pushes the limits of all observation to their breaking point, forcing us to ask if the entire cosmos is merely a shadow on a wall we can never turn away from. Galileo's Hubble lens first pierced the celestial sphere, revealing moons orbiting Jupiter and cracks in the perfect heavens of ancient philosophy. That simple tube ignited a revolution in seeing. Centuries later, Edwin Hubble peered through the 100-inch Hooker telescope and witnessed the galaxies flying apart, their light stretched and reddened, proving the universe was not static but dynamically expanding. He famously described this as the realm of the nebulae, a frontier that redefined our cosmic address. Each leap in technology has torn away another veil. The accidental discovery of the cosmic microwave background by Penzias and Wilson, using a horn antenna built for satellite communication, provided the first tangible evidence for the Big Bang, yet it also presented the horizon problem, a puzzle born from seeing too clearly. The invention of radio astronomy opened an entirely new spectrum, allowing us to listen to the whispers of pulsars and the violent crackle of distant quasars. Then came the Hubble Space Telescope, floating above the distorting atmosphere, and its iconic deep field image. By staring at a patch of sky seemingly empty for days, it revealed a universe teeming with thousands of galaxies, each an island of stars in the profound black. That single image transformed a void into a crowded metropolis. Today, the James Webb Space Telescope peers even deeper, its infrared eyes seeing through cosmic dust to watch the first galaxies being born. We do not just see the cosmos anymore, we feel it. The LIGO and Virgo observatories have detected the ripples in space-time itself, the gravitational waves from colliding black holes, opening an entirely new sense beyond light. Every one of these tools solved old mysteries while revealing deeper, more fundamental puzzles. The cosmic microwave background gave us inflation, which hints at a multiverse. Gravitational waves confirmed black holes, which harbor the information paradox. With every new window we open, we are granted a clearer view of just how much lies in the shadows. What unimaginable instrument will come next? A quantum gravity probe or a neutrino telescope that can truly see the first second of time? Our journey of observation is far from over. It is accelerating, and each new tool promises not just answers, but a new generation of questions that will challenge the very limits of what we can know. These 31 cosmic riddles, from black holes to dark energy, seem to span the entirety of reality, yet they are all bound by common threads. Each mystery, in its own way, exposes the fragile seam between the quantum world and the cosmic stage, revealing a universe where the unobservable is not an absence, but a dominant presence. The physicist Brian Greene often speaks of this grand quest, noting that the deepest truths of the universe may be hidden in the fabric of space and time, awaiting a theory that can weave them together. The Standard Model of particle physics and Einstein's general relativity are monumental achievements, but they are like two different languages describing the same play, one for the actors on stage and one for the theater itself. Where they fail to communicate, a mystery is born. Dark matter and dark energy are the most glaring examples, invisible forces that dictate the fate of the cosmos yet remain completely outside our current physical lexicon. They are not minor anomalies, they are the main characters in the story, and we have been trying to understand the plot by only reading the footnotes. This pattern repeats itself. The hunt for a quantum theory of gravity is a direct response to the singularities where our equations scream into infinity. The search for magnetic monopoles is a testament to the beautiful symmetries in our math that nature seems to have ignored. Each puzzle is a piece missing from a vast jigsaw, and while we cannot see the picture on the box, the shape of the holes themselves gives us clues. The sharp edges of the information paradox hint at a holographic reality. The smooth curvature of inflation suggests a multiverse. To solve them, we cannot simply build bigger telescopes. We need a new kind of detective, one that combines the raw power of better detectors, like next-generation gravitational wave observatories, with the profound leaps of theoretical innovation. This demands an interdisciplinary fusion where cosmologists, particle physicists, and quantum information scientists speak a common tongue. How can we integrate these scattered threads into a single, coherent tapestry of understanding? The answer lies in recognizing that these are not 31 separate problems, but one magnificent problem viewed from 31 different angles, each one a window into the next great revolution in human thought. Each of these 31 cosmic riddles, from the silent pull of dark matter to the ghostly whisper of neutrinos, serves as a stark reminder of the same fundamental truth. Our perception is constrained not by a lack of wonder, but by the very tools we use to see. The universe consistently reveals that what we can observe is merely a fraction of a far grander, stranger reality operating just beyond our current grasp. These are not failures of science, but its greatest triumphs, each paradox a signpost pointing toward a deeper layer of understanding we have yet to uncover. Our journey has shown that the cosmos is under no obligation to conform to our human scale intuitions or our desire for simple answers. In the words of the great astrophysicist Neil deGrasse Tyson, the universe is under no obligation to make sense to you. This is not a statement of despair, but a call to arms for the curious. It liberates us to ask bigger questions, to build more sensitive instruments, and to embrace the beautiful, confounding complexity of it all. The path forward is illuminated by our own relentless curiosity and the technological innovation it inspires. Every new telescope, every deeper underground lab, every more powerful collider is another attempt to listen more closely to the cosmic whisper. So we invite you to carry this sense of wonder with you. Which of these phenomena captured your imagination the most? Was it the frantic search for the missing lithium, the chilling possibility of a false vacuum, or the spooky connection of entangled particles? Share your thoughts and continue the conversation. The exploration is far from over. For more deep dives into the mysteries of space and time, be sure to subscribe. And the next time you find yourself under a clear night sky, remember to look up. You are not just seeing points of light, but gazing into a deep ocean of unanswered questions, a universe that invites us to keep looking, keep questioning, and keep reaching for the stars.